on this slide. On the top, which is the time domain continuous signal, which we are going to sample, which is shown in this as this red waveform. So that's our x of t, our original time domain continuous signal, which we want to sample. So let me write down that. So that's our continuous signal. And that is a signal that we want to sample. Now, the second signal which we have here is called as the sampling function, using which we are going to implement or produce the effect of sampling. So the sampling function is nothing but an impulse train. So we can write the sampling function s delta of t as an impulse train, which is delta of t minus nts for n equals minus infinity to infinity. So that's our sampling function s delta of t, where the amplitude of each of these impulses is 1, and the time separation between the impulses is equal to the sampling period ts, which is equal to 1 upon fs. So that's our sampling function. And by using this sampling function, we can produce the effect of sampling by simply multiplying our continuous signal x of t with the sampling function s delta of t, and that would give us our sampled signal xs of t. So if we see now, because the amplitude of the impulses in the sampling function is are equal to 1 at the sampling instance, that is at 0, at ts, at 2ts, at 3ts, and so on, and similarly at minus ts, minus 2ts, minus 3ts, and so on. So exactly at these sampling instance, the value of the sampling function is 1. At all other time instance, the value of the sampling function is 0. So when we multiply these two signals, that is equivalent to multiplying the amplitude of the signal at the time instant with 1. So whatever is the value here, that gets multiplied by 1, so we get the sample value that is present there. And for all other values in between, the signal value gets multiplied with zeros, so it results in an output of 0. So what we have is effectively the sample signal obtained by multiplying the actual continuous signal with the sampling function, which is nothing but an impulse train. That is a train of impulse functions, or train of delta functions. So we can now write the sample function xs of t. So that's our sampled signal, which is our discrete signal, by the way, and we have obtained that by multiplying the continuous signal x of t and the sampling function s delta of t. So we can write that as xs of t to be equal to x of t multiplied with s delta of t, which is equal to x of t getting multiplied with s delta of t, which is defined as the impulse train, which is delta of t minus nts for n equals minus infinity to infinity, which is simply equal to summation x of nts multiplied by delta of t minus nts. So that becomes our representation or notation for the sample signal in the time domain. So we are looking at this process in the time domain, where we have the time domain continuous signal x of t and the time domain impulse train, which we call as the sampling function. And when we multiply these two, we get our sample signal, which we denote as x subscript s of t. So that gives us our sample function. So analytically, we can represent the sample signal as the product of the actual signal and the sampling function. So again, n ranges here from minus infinity to plus infinity. Now, having seen the analytical representation of the sampling process in the time domain, how do we translate this to the frequency domain and see the analytical representation of the sampling process in the frequency domain? To understand that, we'll use some very basic fundamental principles of the frequency domain and some knowledge, our prior knowledge of the translation from time domain to frequency domain. So, for example, if we have the signal x of t, and if we take the Fourier transform of this signal and convert and get its spectrum, we will represent that spectrum, say for example, by x of f. So that's the frequency domain representation of that signal x of t. We will have it as x of f. So we obtain it by computing its Fourier transform. And similarly, the sampling function s delta of t, its Fourier transform will give us its spectrum. So the Fourier transform of the sampling function would give us the spectrum of the sampling function, which we would denote as capital S delta of f. And correspondingly, the spectrum of the sample signal, again, if we take the Fourier transform of the sample signal, that should give us the spectrum of the sample signal, which we would denote as x sub s of f. Now, rather than taking their Fourier transforms or obtaining the spectrum of the sample signal by taking the Fourier transform of the sample signal itself, we could proceed by obtaining the spectrum of the sample signal using the spectra of the original signal and the sampling function. And to do that, what we do is we will use the property of the Fourier transform, which says that multiplication in the time domain corresponds to convolution in the frequency domain. So here in the time domain, we are multiplying the signal x of t with the sampling function s delta of t. In the frequency domain, that would correspond to convolving their respective spectra. So that means in the frequency domain, if we convolve x of f with s delta of f, that should give us the spectrum of the sample signal xs of f. So we will use this idea to represent the process of sampling analytically in the frequency domain without going into the actual Fourier transformation of the signals x of t and s delta of t and so on. So let's look at that process in the frequency domain now. So now if we denote and represent our original signal spectrum as x of f, and we plot the spectrum here, and if you notice, we are using this triangular shape to represent the spectrum, and that is a very a general procedure in representing a spectrum, because typically most signals have the magnitudes of lower frequencies to be higher, and as the frequency goes up, the magnitude tends to become smaller and smaller and smaller. So the magnitudes of the higher frequency components are usually weaker than the magnitudes of the lower frequency components, and hence the general representation of spectrum for a baseband signal is represented in this triangular form. Again, it could be some other shape as well, but in general, for most practical signals, it is noticed that lower frequency components have higher magnitude, and as the frequency increases, the magnitude of the higher frequency components gets lower and lower. So we denote this as a triangular shape, right? So we have this which is the spectrum of our continuous signal, which has a highest frequency component of f max. And then we have here the spectrum of the sampling function, which is the sampling function is an impulse train, and the spectrum of an impulse train is also an impulse train, but in the frequency domain. So since we had the sampling function denoted as summation of delta of t minus nts, its spectrum would be also an impulse train, but in the frequency domain as delta of f minus n fs. So s delta of f would be, I'll just write it here. So s delta of f is nothing but, that's equal to summation delta of f minus n fs, and for n equals minus infinity to infinity. But now when we take this spectrum, it has a scaling factor of 1 by ts, or simply fs. So that's a scaling factor we get with the spectrum in the spectrum of the sampling function. So we've denoted that here. So the amplitude of each of these pulses in the frequency domain that you see is fs equals 1 upon ts. So that's the spectrum of the sampling function, s delta of f. Now in the frequency domain, the equivalent process of multiplying the time domain signals is convolution. So multiplying x of t and s delta of t corresponds to convolving x of f and s delta of f. So the process that's going to happen here between these two spectra is convolution. So convolving these two will produce our spectrum of the sample signal, which we denote as xs of f. So the spectrum of the sample signal, so let's write here, xs of f is nothing but the convolution of the spectrum of the original signal x of f with the spectrum of the sampling function s delta of f. And by the way, the sampling operation or the convolution operation is denoted by the star inside the circle. So I'm using the star inside the circle to denote the convolution operation. So the spectrum of the sample signal is obtained by convolving the spectrum of the original signal with the spectrum of the sampling function, so which is equal to x of f convolved with summation, right, I'll use that, fs summation delta of f minus n times fs, where n goes from minus infinity to plus infinity. So that is the analytical representation of the sample signals spectrum, and we could simplify that as simply fs into summation of x of f minus n fs, where n goes from minus infinity to plus infinity. Now if you notice here, when n equal to 0, you will get x of f scaled by fs. So again, one thing I need to write here is that this should be fs, which is 1 by ts. So when n equal to 0, we simply get this term as x of f, which is this term. When n equal to 1, it is x of f minus 1 fs. That means it is a shifted version of x of f by 1 fs. So that is that term. again it is going to have a magnitude of 1 by ts, which is fs. And when n is equal to 2, it is x of f minus 2fs, which is this term here, this representation here, this replica. And similarly, when n is equal to minus 1, it will be x of f minus fs, so x of f plus fs, which is a left shifted version here. So we have this term when n equal to minus 1, and similarly when n equal to minus 2, we have this term, and so on. So n ranges from minus infinity to plus infinity, and I've just depicted here for n equal to minus 2, minus 1, 0, 1, and 2. So what we see is that the spectrum of the sampled signal contains basically the spectrum of the original signal and replicas of it at integer multiples of the sampling frequency, but obviously they are scaled by the scaling factor, which is 1 by ts. Now again, what I have depicted here corresponds to the case where the sampling rate fs is greater than 2f max. So this part here is f max, and that is minus f max. So that distance is also f max, that distance is also f max. So here fs is greater than 2f max. So what I have drawn here, or the analysis that I made here, is for the condition that the sampling rate fs is greater than twice f max, or it is greater than the Nyquist rate. So we see in the analytically now that the process of sampling indeed produces a spectrum where the spectrum of the sample signal contains replicas of the original continuous signal spectrum at integer multiples of the sampling frequency.